Good morning to all. Myself, Kalai Selvi, working as Assistant Professor Selection Grade 1 in the Department of Computer Science and Engineering at Erode Sengunthar Engineering College. In today's class, we are going to discuss about the subject Digital Electronics. In this subject, we are going to cover the topic Combinational Circuits. And also, we are going to discuss some of the gate questions which comes under this topic. Combinational circuit. First, digital system. Digital system is a system which processes the binary information, and this digital system is classified into two types. One is the combinational circuit and sequential circuit. Sequential circuit is further classified into two types. One is synchronous sequential circuit and another one is asynchronous sequential circuit. In today's class, we are going to concentrate on the topic combinational circuit. Combinational circuit is combinational logic. First, we'll see the definition of combinational circuit. Combinational circuit consists of input variables, logic gates, and output variables. We can also give the definition for this combinational circuit as the circuit whose output depends upon the present combination of inputs. So here is the block diagram of the combinational circuit, which takes n inputs and produces m outputs, and these m outputs depends upon the present combination of inputs. And some of the example of combinational circuits are half adder, full adder, half subtractor, full subtractor, encoder, decoder, multiplexer, demultiplexer, magnitude comparator, and so on. Combinational circuit consists of two procedures. One is the analysis procedure and another one is the design procedure. Analysis procedure deals with analysis of or finding out the Boolean function and the truth table. Design procedure deals with we have to find out the circuit for a given problem statement. First, we will see the analysis procedure. After that, we will discuss the design procedure. Analysis procedure, as I already said, we have to find out the Boolean function and the truth table. So, for this analysis procedure, a circuit will be given. For that circuit, we have to identify the Boolean function and the truth table. So, what are the steps to obtain the Boolean functions? So, here we'll see the steps to obtain the output Boolean functions from a logic diagram, which is as follows. Label all gate outputs that are a function of input variables with arbitrary symbols. Determine the Boolean functions for each gate output. Label the gates that are a function of input variables and previously labeled gates with other arbitrary symbols. Find the Boolean functions for these gates. Repeat the process outlined in step 2 until the outputs of the circuit are obtained. By repeated substitution of previously defined functions, obtain the output Boolean functions in terms of input variables. So this is an example circuit diagram we are going to consider. So we have to apply the analysis procedure for this circuit diagram. So we have to find out the output Boolean function and the truth table for this circuit diagram. That is the analysis procedure. Here, the circuit diagram consists of the logic gates, AND gate, OR gate, NOT gate, and which takes the inputs A, B, C and the output F1 and F2. Here, some of the variables are mentioned as T1, T2, T3. That can be considered as the temporary variables or temporary Boolean functions that may be considered as the output of a gate. So with the help of this temporary variables, we can able to find out the final Boolean functions. So, we are going to apply these steps which we have discussed here. All these 4 steps have to be applied in this example circuit. So first, all the input variables are given, which is A, B, C, and this T2. T2, what is T2? So the AND gate expression is T2. T2 can be written as T2 equal to A dot B dot C, and this T1 T1 is an output of an OR gate. So for OR gate expression, we can have the expression for T1 as T1 is equal to A plus B plus C. And here if we need, we can use the temporary variable T4, T5, T6 and all. Otherwise, we can write the expression directly, and we can say the output of this OR gate is the combination of the three expressions of AND gate. So that can be considered as F2, that is AB plus AC plus BC. That is, here the OR gate AND gate expression will be AB, output will be AB. Here it is AC, and for this AND gate it is BC. And for this OR gate expression, for this OR gate output, will be having the expression as AB plus AC plus BC. That can be considered as F2. And this F2 is given as input to the NOT gate. So this NOT gate output is F2 dash. And here is an AND gate. This AND gate output is considered as T3. So this AND gate takes the input from T1 and F2 dash. So we can write the T3 expression as T1 dot F2 dash. So here it is T3 is written as F2 dash dot T1. And the final Boolean function F1 is considered as the input is T2 and the T1. So here we can have the F1 expression as F1 is equal to T1 plus T1, sorry, not T1, it is T2 plus T3. So we are having the intermediate variable expressions, which can intermediate variable expressions can be said to be an arbitrary symbols. So here are some of the arbitrary symbols involved. So here we can write the final Boolean function in terms of input variables. So we can write function F1 as F1 is equal to, it is okay. So it is F1 is equal to it is a combination of T2 and T3. That is the output of the OR gate. That is T2 plus T3. And what is T2? T2 already we have found that T2 is ABC. It is ABC. And what is T3? T3 is, that also we have found already, it is F2 dash T, and this function consists of two terms, ABC and F2 dash T. ABC is truly combination of the input variables, and the next term F2 dash T, it consists of some arbitrary symbols. So we have to convert these arbitrary symbols into in the form of input variables. So we have to substitute the value of F2 and take complement, so we can get F2 dash, and we have to replace the values of T1. So here ABC can be considered as such. It is ABC, and F2 dash is F2 is AB plus AC plus BC whole dash into T1. T1 is A plus B plus C. So it is into A plus B plus C. So after this, we have to apply the De Morgan's law. So first ABC is considered as it is. We have to apply De Morgan's law here. So after applying, we'll be getting A dash plus B dash dot and A dash plus C dash dot B dash plus C dash into A plus B plus C. A plus B plus C. So here we have to apply the distributive property. So after applying the distributive property, we will be getting the function in terms of the input variables, all the terms in the form of input variables. So we can say the function f1 as A dash B C dash plus A dash B dash C plus A B dash C dash plus ABC. So or the final Boolean function is in the form of the input variables, and f2 is also in the form of input variables AB plus AC plus BC. So we have to consider only the input variables in the final expression, that is in the final Boolean function consists of only the input variables. So this is the Boolean function which we have obtained. And next is the truth table. So how we are going to obtain the truth table for this circuit diagram. So consider here it is the circuit diagram. It is a combination of 3 inputs. So 3 inputs A, B, C, and number of rows for this 3 input function will be 2 power n by applying the formula 2 power n. 2 power n. So 2 power n, n is equal to 3 means 2 power 3. 2 power 3 is 8. So 8 rows. This truth table consists of 8 rows. By using this formula, we have find out that this truth table consists of 8 rows. And how we are going to find the values for this rows? So that for that also we are having the formula which is 0 to 2 power n minus 1. 0 to 2 power n minus 1. So it can be said to be 0 to 7. So 0 to 7. So 0 to 7 is a decimal value, and this decimal value we have to consider the binary value. Converting this decimal into binary, will be getting the values 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on up to 1, 1, 1. So we have to consider the binary value of this 0 to 7 in 3-bit representation. So we can have the values here, and we have to find the intermediate columns. Intermediate columns, temporary variables, that is T1, T2, T3 can be found out, and we can find the final Boolean function F1 column. Okay. So we have to substitute the values here by using the truth table of the logic gates, AND gate, OR gate, NOT gate. These logic gates truth table have to be used to obtain the truth table of the given circuit diagram. Next is the design procedure. Design procedure is the procedure from which we can able to get a circuit diagram. So these are the steps. Design procedure of combinational circuits, or state the problem. From the specification of the circuit, determine the required number of inputs and outputs and assign a symbol to each. Derive the truth table that define the required relationship between inputs and outputs. Obtain the simplified Boolean functions for each output as a function of the input variables. Draw the logic diagram and verify the correctness of the design. So here for the design procedure, the problem statement will be given. From that problem statement, we have to determine the number of inputs and the output. With the number of inputs and output, we have to derive the truth table. and we have to obtain the Boolean function for the truth table by using a Karnaugh map. We have to draw the circuit diagram. So these are the steps for the design procedure of the combinational circuit. Here is an example of a design procedure. A simple example. Design a logic circuit that has three inputs A, B and C and whose output will be high only when a majority of the inputs are high. So this is the problem specification given. From this specification, we have to identify the number of inputs and the output. After identifying the number of input and output, we have to form the, or we have to set up the truth table. So from here, it can be easily found that from the question itself, it is mentioned that three inputs, which are A, B and C, and output can be considered as one output. So for three inputs, as we discussed in the previous analysis procedure, three input means which takes the 8 rows and the values of the rows will be from 0 to 7. So in this way, we have formed the input columns of the truth table. And how we are going to obtain the output means, so from the specification, we have to understand whose output will be high only the majority of the inputs are high. So the output will be high when the number of inputs are more number of inputs. That is, if you are having more number of ones in the input, then the output will be 1. That is the specification given. So with that specification, we have to write the output column. So here it is for first row, it consists of zeros, all the zeros. So here does not have any 1. So we can, it is not possible to find the majority of inputs with high. So it is considered as 0. And next input 0, 0, 1. Here the majority of inputs are 0. So the output is also 0. And for the third row, it is 0, 1, 0, 0, 1, 0. Here also the majority of the inputs are 0. So the output is 0. And 0, 1, 1. Here 0, 1, 1. The majority of the inputs are 1. So the output is 1. And here the majority of the inputs are 0. So the output is 0. And for 1, 0, 1. In this 1, 0, 1, the majority of the inputs are 1. So output is 1. 1, 1, 0. It is here also the majority of the inputs are 1. And 1, 1, 1. It is also, we can say that the majority of the inputs are 1. So the output is 1. So we from the specification, we have formed the truth table for the problem. After forming the truth table, we have to find the Boolean function. So how we have to find the Boolean function? With the help of the Karnaugh map, we can able to find the Boolean function. So how we are going to apply the K-map. So for this output column, from the output column of the truth table, we have to find the sum of minterms. So whichever row is having 1, that is whichever minterm is 1, that can be considered here, and we can write the sum of minterms for this truth table as f is equal to, or here the output is x, so we can consider x is equal to summation of, so here it is 1, the minterm is 0, 1, 1 is m3, so we can say 3, summation of 3 comma, here it is 1, so its minterm is 1, 0, 1, 1, 0, 1 is 5, so 3, 5, and the next minterm is 6 and 7. So this is the sum of minterm for this truth table. So we have to simplify this using the K-map. So the number of inputs are 3. So we can use the 3 variable K-map. The 3 variable K-map can be used here. 3 variable K-map. So here, this is the 3 variable K map. The row variable is A. Sorry, here it is A, and the column variable is BC, and it is A dash A, and this one is B dash C dash, B dash C, BC, and BC dash. So this is the K map. So we have to plot the minterms in this K map. 0, 1, 2, 3, 4, 5, 6, 7. So after plotting the minterms, we have to map. So in K map, for a 3 variable K map, we have to see the first possibility of mapping as octet possibility. So here we don't have the octet possibility. Octet is nothing but the 8 adjacent cells. We don't have the combination of 8 adjacent cells here. And the next possibility is quad possibility. Quad is nothing but the 4 adjacent cells. Here also we don't have the possibility of quad. After quad, we have to go with the checking the possibility of pair. So here we are having the pair possibility. So how many pairs are here? So it is 1 pair, and this is another 1 pair, and this is the next pair. So we are having 3 pairs here, and that's all about the mapping. Then we have to write the Boolean function for this pairs. So this pair is BC. That is when mapping, considering these this pair, this A and A dash will be A dash plus A will be 1, and the remaining BC will come here. And for this pair, when we are mapping this pair, will be having, we have to consider this B dash C and BC in this the odd term, or B dash plus B. So B dash plus C is considered as 1, and the remaining variable is C here, and in this row we are having A. So we can write as AC, and similarly for this pair will be having A, B. Here for this pair, this C plus C dash will be 1, and the remaining A and B are here. So the term is AB. So the Boolean function for this problem is F is equal to BC plus AC plus AB. And after finding out the Boolean function, we have to draw the circuit diagram for this Boolean function. So this is the circuit diagram for the Boolean function. 3 inputs A, B, and C, and the output is BC plus AC plus AB. So B and C are connected to AND gate, A and C are connected to AND gate, and A and B are connected to AND gate, so that the output of AND gate have to be given as input to the OR gate. So the final output from the OR gate, it is considered as the expression X is equal to BC plus AC plus AB. So in this way we have to draw the circuit diagram. So for design procedure, problem statement will be given. From that problem statement, we have to identify the number of inputs and the output. After identifying the number of inputs and outputs, we have to derive the truth table. We have to obtain the Boolean function. Boolean function can be obtained with the help of the Karnaugh map. And finally, we have to draw the circuit diagram. So this is one example, and here is the another one example. So this is the design procedure problem for BCD to XS3 code. So BCD input is considered as the BCD input, and the output is considered as the XS3 code output. Here we are considering the input as 4 input BCD values for each and every individual decimal digit. The BCD representation should be given as 4-bit representation. So the input is considered as a 4 input. So for 4-bit, we can have the values from 0 to 9, because for BCD representation, we have to consider the values from 0 to 9. It consists of single decimal digit, so that it is possible to represent the decimal digit with 4-bit binary representation. If we are going with 10, means from 10 to 15, it consists of two decimal digit. So for that 2 decimal digit, it is not possible to represent with 4-bit. So we are considering only from 0 to 9. And the remaining 10 to 15 can be considered as the don't care condition for BCD input. And what is the output? Output is an XS3 code. So here it is 0, 0 XS3 is 0011. That is, for in simple way, you can say it is 0. So 0 plus 3. 0 plus 3. X3 is extra 3. We have to give extra 3 to the input. So 0 plus 3 is 3. So 3, the binary representation of 3 in 4-bit is 0011. Okay. So next is 0001. So it is 1. So 1 plus 3. 1 plus 3 is equal to 4. So 4, binary representation of 4 is 0100. So in this way, we have to write the input and the output of the truth table. After finding the writing or forming the truth table of this code conversion BCD to XS3 code, we have to find out the Boolean function. So here we are having 4 output columns. So for this each and every for this 4 output columns, we have to find the Boolean function separately using the Karnaugh map. After finding the Boolean function separately using the Karnaugh map, we have to draw the circuit diagram as a single circuit. So this W, sum of minterms for this W column is W is equal to summation of where the 1 comes for the minterms here. So it is 5, 6, 7, 8, 9. So 5, 6, 7, 8, 9. And with don't care 10 to 15. So 10 to 15. Similarly, we have to write the sum of minterm for X, Y, and Z. After finding the sum of minterms, we have to use the Karnaugh map for the X, W, X, Y, Z variables. That is the output functions. So this is the Karnaugh map we have found. And after with the help of this Karnaugh map, we can able to get the Boolean functions. After getting the Boolean functions, we have to draw the circuit diagram. So this is the circuit diagram for the code converter BCD to XS3 code. So here in this Karnaugh map, we have to consider the minterms 10 to 15 as don't care. So we are representing the don't care condition as X here. So X, if we want to include this don't care in our mapping, means we can consider this don't care value as 1. Otherwise, it is considered as 0. Wherever it is necessary, we can include that. If not necessary, we don't bother about that. So only it is named as don't care condition. So it is a 4-variable K map. In this K map, 4-variable K map, we have to go with the possibility of, first we have to check with the possibility of 16 adjacent cells. All the 16 adjacent cells have to be mapped. After checking with the 16 adjacent cells, we have to go with checking the possibility of octet, after that quad and pair, and after that single ones. So in that way, we have to make the mappings in the K map so that we can find out the Boolean functions as like this. For Z, it is D dash. Here it is a possibility of octet possibility. And for Y, it is 2 quads. So this is 1 quad and this is another 1 quad. For this quad, it is CD, and for this for this quad it is C dash D dash, and for this quad it is CD. And here for this octet will be having all these row variable will be considered as 1, and in this first column and last column the different terms are here it is C dash and it is C. So C plus C dash becomes 1 and the remaining is D dash. So here it is Z equal to D dash. And here also for this 2 quad possibility, this all the row variable A, B or the row variable, this row variable is will be 1, and here it is C dash D dash and this one is CD. And for this X we are having one quad here, another one quad, and this is another one pair. So for this quad we will be getting the different variables A dash, here it is A, so A dash plus A becomes 1, so remaining is B dash, and here it is C dash plus C. C dash plus C is 1 and the remaining variable is D. So we will be getting D dash D for this quad, and for this quad we'll be getting B dash C, and this pair it is 0, that is here it is A dash, it is A, so A dash plus A is 1, so the remaining is B, so BCD, we will be getting BCD, the third term, the pair term is BCD. So X is, the Boolean function for X is equal to B dash C plus B dash D plus BCD. And for W, yeah, we will be getting a octet here. Here is an octet possibility, one octet possibility. This is an octet possibility, 8 adjacent cells, and this is a quad possibility, and here is another one quad possibility. So one octet possibility and 2 quad possibility are there. So for this octet possibility, the column variables becomes 1 and the row variable here B plus B dash becomes 1 and the remaining is A. So first term we are having A, and this for this quad will be having A dash plus A becomes 1, remaining is B, and here C dash plus C becomes 1, remaining is D. So we'll be getting BD. This quad is BD, and for this quad it is B and C, BC. So the expression for W is equal to A plus BC plus BD. So in this way, we have found out the Boolean function, and after finding the Boolean function, we have to draw the circuit diagram. So this is the circuit implementation for BCD to XS3 code converter. If necessary, we can simplify the Boolean expressions. If you are aware of that, you can simplify, or if you are struggling with that simplification, means you can directly draw the circuit diagram, no problem. But whenever simplification is necessary, you have to make simplification so that only the complexity of the circuit diagram will be reduced. The next is binary adder-subtractor. So adder, half adder, full adder, half subtractor, full subtractor is considered as the example for combinational circuit, and by considering both we can say the circuit as a binary adder-subtractor. So first here we are going to cover the half adder and the full adder. Half adder is a combinational circuit that performs the addition of 2 bits, addition of 2 inputs, that is called as half adder, and the output of this half adder is the sum and carry output. So for this half adder also we can follow the design procedure of the combinational circuit. So it is the addition of 2 inputs. So we have to use the binary addition rule for forming the truth table for this half adder. So two bits. So we are saying as 2 bits or 2 inputs. So the number of input for this half adder is 2, and the number of output is 2. That is sum and carry. So the 2 input takes the values 0, 0, 0, 1, 1, 0, 1, 1, and by using the binary addition rule, we can say the sum and carry as the output. So 0 plus 0 is 0. Both the sum and carry are 0, and 0 plus 1 is 1. Sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. 1 plus 1, 1 plus 1 rule is 0 with carry 1. So we can say sum is 0 and carry is 1. And here also we can find the Boolean function using the Karnaugh map. So here we can write the sum of minterms for this sum and carry as S is equal to summation of where we are getting 1 in the output of yes. So here it is 1, here also 1. So the corresponding minterm is m1 and m2. So we can write it as 1, 2. And for carry, we can write the sum of minterms as C is equal to summation of. So in C column where we are getting the 1, so it is here. So the corresponding minterm is m3. So we can write it as summation of 3. So as it is a 2 input, so we can have the 2 variable K map to get the Boolean function for this half adder. So the 2 variable K map can be represented like this. So we have to draw the separate K map for sum and carry. So here first we will find the sum and next we will find the carry. So here we can represent the x variable in the row and y variable in the column. So this first row is x dash and x, here it is y dash and y, and s is equal to summation of 1, 2. So we have to map, we have to plot the values, that is 0, 1, 2. So in this 2 variable K map, we have to check with the possibility of quad possibility. So we don't have any quad here. Next we have to check with the pair possibility. We don't have any pair possibility here. So the last is pair. So we are having the single one possibility. We don't have quad possibility and we don't have pair possibility here. So we are going with the single one possibility. So here is a single one and here is another single one. So we can write the sum expression as S is equal to, so this can be written as x dash y, and this single one can be written as x y dash. So this can be simplified as x plus with circle y. That is x plus with circle. Plus with circle is XOR operator. So XOR y. We can say in other word x XOR y or x plus with circle y. So the sum expression is S is equal to x XOR y. Similarly, we can find the expression for C, that is carry. For carry also, we can use the 2 variable K map. So this is for carry. It is x dash x and here y dash y. Here the minterm, only one minterm is available in the available in C. So we can plot the value 0, 1, 2, 3. So here the only possibility is a 1 singles. So we can write C value as x is equal to, sorry, C is equal to xy. So we have found the Boolean function for sum and carry. So after finding the Boolean function, we can draw the circuit diagram. So this is the circuit diagram, implementation of half adder. So this follows this half adder, full adder, all follows the design procedure of combinational circuit. So here we are having 2 circuits. So this is before simplification. So this is after simplification. See here, before simplification we are using 3 AND gate, 1 OR gate, whereas for after simplification we are using only 1 XOR gate and 1 AND gate. So simplification makes the circuit easier for implementation. So this is implementation of half adder. And next is full adder. Full adder, it takes 3 inputs and produces 2 output. So full adder, one that performs the addition of 3 bits. There is 2 significant bit and a previous carry. We can say like this. It is a full adder. So which takes 3 inputs. 3 inputs means the number of rows in the truth table will be 8 and the combination of values will be from 0 to 7. For this output is same as half adder, sum and carry. So for finding the sum and carry, we have to use the same binary addition principle which we have used in the half adder. So by applying the binary addition rule, we'll be getting the sum column and carry column like this. For example, all 3 zeros. So 3 zeros gives sum 0, carry 0. And here 0 plus 0, 0. And again 0 plus 1. Sum is 1, carry is 0. And here it is 0 plus 1. Partial sum is 1. And 1 plus 1 is 0 with carry 1. So here the sum is 0, carry is 1. Suppose we are considering the 1, 1, 1 input. 1 plus 1. 1 plus 1 is partial sum is 0 with carry 1. And here you will be having another 1 here, and also we have to add the carry bit, carry 1 with this one. So 0 with carry 1. For here 1 plus 1 is 0 with carry 1. Partial sum is 0, carry is 1. So here carry is considered as 1. And partial sum is 0. That partial sum have to be added with this z value. So here it is 1. So 0 plus 1 is 1. So carry is 1 and also sum is 1. So in this way, we have formed the truth table for this full adder circuit. After forming the truth table, we have to write the sum of minterms for sum and carry. For sum, we can say S is equal to summation of 1, 2, 4, 7. And for carry, we can say C is equal to summation of 3, 5, 6, 7. So after finding the sum of minterms, we can simplify the sum and the carry expression with the help of the Karnaugh map. Here the input is 3 input. So we have to consider 3 variable K map. So this is the 3 variable K map we are using. And for the sum, so sum it is 1, 2, 4, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So there is no possibility of octet, quad and pair. All are single ones. So while writing the answer, final Boolean function is S is equal to x dash y dash z plus x dash y z dash plus x y dash z dash plus x y z. So this is sum expression, and the carry expression is, so carry equal to summation of 3, 5, 6, 7. So while plotting this in K map, we'll be having 0, 1, 2, 3, 4, 5, 6, 7. So here we are having 3 pair possibility. So we can write the C expression as C is equal to xy plus xz plus yz. And so this is the circuit diagram for the expression which we derived here. So this is full adder implementation. So we can implement the full adder with the help of 2 half adder and an OR gate. Mostly we are using this circuit only. We are not using this circuit. So this is the simplified circuit. We can say it is the full adder circuit with 2 half adder and an OR gate. So how we are deriving this? We have to simplify the expression. So actual expression is this. Actual expression is this. So in this first two term, they are considering the z dash as the common variable. So z dash into xy dash plus x dash y. And in this two term, they are considering the z as common variable, taking z as common, and we can write z into xy dash plus x dash y. Okay. That is z into xy plus x dash y dash. That xy plus x dash y dash can be written as like this, xy dash plus x dash y the whole dash. Here we can say here. So this is here we are considering z dash as common, and we are writing xy dash plus x dash y. And in this two term, considering z as common, we can write xy z into xy plus x dash y dash. So this can be written as z dash into x plus with circle y plus z into, this can be written as x plus with circle y the whole dash. Okay, and this x plus with circle y can be considered as a temporary variable t. We are assigning this expression to a temporary variable t. So we will write the expression as z dash t plus z t dash. Again, it is in the form of XOR expression. So you can write z plus with circle t. So what is t? T is x plus with circle y. So we can write z plus with circle, replace this t with x plus with circle y. So we can write z plus with circle, x plus with circle y. So we can write x plus with circle, y plus with circle z. So this is the way we have derived this expression. So this is a simplified Boolean expression. So as I already said, wherever simplification is possible, you can make the simplification so that the circuit can be implemented easily. Otherwise, it is a complex one. So S expression is x plus with circle, y plus with circle, z. And C, for C also, carry expression also, we can write it as for getting the simplification. So actually, we are having the expression like this, xy plus xz plus yz. So in order to implement the full adder with two half adder and an OR gate, so we are considering this xz as xy dash z and yz as x dash yz. Without making the pair combination, we are considering the single ones here. So this one is considered a single one, this one is considered a single one, and we are making the pair possibility for this one only. So here we are considering the expression for C as like this, so that we can implement the implement the full adder with two half adder and an OR gate here. So here in this we are considering z variable as a common variable. We are taking z as common, so we can write z into xy dash plus x dash y. So that is the thing we are written here, and plus xy is available here. So after simplification, that is this xy dash plus x dash y can be written as x plus with circle y. So x plus with circle y. So here you can write the C expression as, what is the C expression here? That is this one. That is x plus with circle y into Z. This one is Z. So this is X plus with circle Y. X plus with circle Y. X plus with circle Y into Z. Then this one is this XY. Here we are having XY here. So we can write the C expression as C is equal to XY plus Z into X plus with circle Y. X plus with circle Y. So making C expression as like this, it is possible to implement the full adder circuit with 2 half adder and an OR gate. So this is the implementation of full adder with 2 half adder and an OR gate. See here, this is one half adder, this is another one half adder, this is an OR gate. We know the implementation of half adder is this one. After simplification, we are implementing the half adder circuit as like this. So this is the half adder. So here, this is one half adder, this is another one half adder, this is OR gate. So this is the way we have implemented the full adder with 2 half adder and an OR gate. Next is NAND implementation and NOR implementation. We say that NAND and NOR gate are the universal gate. So why we are saying it as universal gate? Whatever gates, whatever logic circuit with which is represented with the basic gates AND or NOT can be expressed with the help of this NAND gate and NOR gate. So NAND and NOR gate are said to be the universal gates. So these are the representation of the NAND gates for the basic gates. NOT gate can be represented like this for NAND with NAND representation, and AND representation is given like this. AND can be represented as NAND like this, and OR gate can be represented as like this for NAND representation. And this is NOR representation. It is dual of NOR operation is dual of NAND operation. Here and or not, all these gates are represented as NOR gates like this. And how this AND OR circuit diagram can be converted into NAND gate and NOR gate. So this is the steps for converting the AND OR circuit diagram into NAND gates. This is, and for NOR gate, this vice versa. These steps have to be followed vice versa. Here, to convert a multi-level AND OR diagram into an all NAND diagram using mixed notation is as follows. Convert all AND gates to NAND gates. First, we have to convert the all AND gates to NAND gate with AND invert graphic symbols. And second step, convert all OR gates to NAND gates with invert OR graphic symbols. Third step, check all the bubbles in the diagram. For every bubble that is not compensated by another small circle along with the same line, insert an inverter or complement the input literal. So these are the steps we have to follow for converting the AND OR circuit diagram to NAND diagram. We can convert all the AND OR NOT gates to NAND gates. So here are some gate questions. First question, design a half adder using NAND and find the minimum number of NAND gates required. And design half adder using NOR and find the minimum number of NOR gates. So we have to convert the we have to design the half adder using only the NAND gate and using only the NOR gate, and we have to use minimum number of NAND gates and NOR gates. And the solution is, so actual circuit diagram for the half adder is this one. which consists of two inputs A and B, and the output sum and carry. So which is our sum expression is given as sum is equal to A plus with circle B, and carry expression is given as A dot B. This is the actual implementation. So we have to convert this XOR gate and AND gate into NAND gate and also to NOR gate. So first, for this sum is x plus with circle y. As we already discussed that the expression for sum is x plus with circle y, and that x plus with circle y can also be represented as x dash y plus xy dash. So the circuit diagram with AND or NOT gate for the x plus with circle y expression is like this. So this is x y dash. This AND gate is x y dash. For this AND gate, it is x dash y, and connecting these two outputs to OR gate, we will be getting x dash y plus x y dash. So that can be written as x plus with circle y. So by following the steps which we discussed in the previous slide, for converting the AND OR circuit to NAND gate, we have to include, or we have to convert the we have to use that is, we have to convert the AND gate to NAND gate. AND gate is converted to NAND gate by adding bubbles at the output, and OR gate can be converted to NAND gate by using the bubbles in the input side, so that it can be converted to NAND gate. And here also this NOT gate can be converted to NAND gate, and here also this NOT gate can be converted to NAND gate. So as we have to implement with minimum number of gates. So we have to consider this AND gate, a single input, NOT gate. It is not an AND gate, it is a NOT gate. So we have to, instead of considering this NOT gate as single NAND gate and this NOT gate as single NAND gate, we are considering both these two NOT gates as a single NAND gate here. So this is the NAND gate implementation for this expression only, but we have to use we have to convert the half adder into NAND gates. So here the expression is considered only for the sum. We have to include carry also. So for this, we can have the carry also here. So this is the NAND gate representation, which takes 5 NAND gates. So this is sum expression and this is carry expression. So totally 5 NAND gates are required to implement a half adder. And also in the same way, so it is a reverse, vice versa, for NOR implementation, vice versa operation of NAND implementation have to be followed, so that we can have the 5 NOR gates to implement the half adder. So this is the minimum number of gates. So minimum number of gates required for implementing half adder using NOR gate and NAND gate is 5 gates. That is the solution. And the next question is, a number of full adder and half adder are required to add 16-bit numbers is. For adding 16-bit number, how many number of full adder and half adders are required? That is the question which is asked. For this 16-bit number, while adding the LSB, the least significant bit, so the starting bit, that consists of only 2 bits. So for adding 2 bits, it is enough to use one half adder. When the half adder produces a carry, that have to be included in the previous bit. Previous bit of the LSB. So there we are in need of a full adder. There comes a 3 input combination. So we have to use full adder circuit there. So last 16 bit, that is the LSB. LSB can be added with one half adder, and the remaining 15 bits before that last LSB can be implemented with full adder. So we are in need of 15 full adders. So the solution for this question is the number of full adder and half adders required to add 16-bit number is this one. B is the answer. 1 half adder and 15 full adders. So for adding the LSB of the 16-bit number, it is enough to use half adder. LSB can be added with the help of the half adder, and the bits before to that LSB have to be used or added with full adders, because the LSB of the 16-bit number produces a carry, and also all the LSBs, all the bits before that LSB, final LSB will produces the carry, so that it can be considered as the 3-bit 3 inputs. So for 3 input or a 3-bit number, full adder have to be used. So we are in need of 1 half adder and 15 full adder for adding the 16-bit number. That's all. Thank you. Thank you for your patient listening. Thank you all.